Hello, boys and girls. I'm back with you on the discussion of Bayesian inference. You see that it's a very historic topic. I mean, the Bayesian inference. It starts long back from the year 1760 onwards, quite older than the classical statistical inference. So a lot of issues, lot of controversies, lot of debates on that, whether the Bayesian inference is much better than the classical inference and other things. But what I can say that till 1990 it was not that much popular, but after that in 1990 people get more inclined to Bayesian inference than the statistical classical inference. So what my objective here that in the first part of our discussion I will go for only the selection of priors, how it behaves and how it can be used for the analysis, and then we will go for some interval estimation and the other inferences like testing and other things. And then in the second, then we go for ultimately in the second section and other things, the extension of these Bayesian inferences, and then finally we go for the computation techniques there. All right. So let's start with the first session. So prior selection is a very important issue, and there are varieties of priors. And what I am going to do that to recapitulate that selection of priors or the varieties of priors, then I will discuss briefly over that and go for then the posterior analysis. All right. So basically the problem that arises is to specify a prior distribution for a parameter about which nothing is known. Whenever you have a finite set, it does not make any problem, because in this finite set you can, for every point you can assign equal probability. So, but whenever you have a continuous interval and maybe even in the real line, if you assume equal probability, that does mean that you are considering a uniform prior on the entire real line or on a particular interval a to a plus h. So that leads to an improper prior. I mean the prior for which the integration does not exist. Okay. And for the scale parameter similarly, one can have the improper prior 1 over sigma. For the parameter sigma you have the prior 1 over sigma. But that is the problem, you know, that the problem is that with the uniform prior it loses the invariance property on the scale parameter. The reason is that I can explain that if you have the pi theta to be or p theta to be 1, then if you, I mean I am assuming this prior because I do not have any idea about the theta parameter behavior. So I assume that at every point theta takes the same probability. So with this, if you go for some scale transformation like gamma equals to g theta equals to log theta, you will see that prior the transformed prior is not free from theta. I mean now it is a function of gamma. So it ultimately stands the prior parameter or prior distribution of gamma comes out to be e to the power gamma. So whatever uniform prior that we have assumed for theta is not really true for gamma. So this is the limitation of considering the uniform prior, that it loses the invariance property. And then to skip this thing, rather to deal with this thing efficiently, Jeffrey developed this prior. Jeffrey's prior is based on the information matrix. So p theta is proportional to I theta to the power half, where I theta is the Fisher information matrix. For example, I can show you that for the binomial setup, one can compute the Jeffrey's prior, and that comes out to be I theta to the power half, which is theta to the power minus half and 1 minus theta to the power minus half. So it's a beta density with parameters half and half. For other distributions, the Jeffreys prior can be computed. That is, for Poisson distribution, you can see for normal distribution, for normal with parameter mu, and you see that pi mu comes out to be 1. For normal distribution with scale parameter sigma, you see that pi sigma is 1 over sigma. So improper prior usually in many situations lead to proper posterior. As long as the posterior is proper, there is absolutely no problem. You can make the posterior inferences and can construct the credible intervals or other things. But so long as the improper prior leads to improper posterior, that creates the problem. So one has to be careful about using the improper prior. Another example is there where x1, x2, xn are observations from Poisson distribution, and the prior distribution is this, root 1 by root over theta. And then you see that the prior is divergent in the sense that it's improper. So 0 to infinity pi theta d theta is infinity. Even if it is improper, the posterior density comes out to be a proper distribution. In fact, the posterior density of theta is gamma half plus summation xi and n. So this is about the normative or about the objective prior. The subjective prior is very much controversial, although many people believe in the subjective choices of prior. And also, as I said earlier in my introduction, that one cannot skip subjectivity, whatever stage you are considering for the prior. Maybe it is objective, but the hyperparameters are subjectively needs to be chosen. The problems with the subjectivity: what if the prior and the likelihood disagree substantially? The subjective prior cannot be wrong, but may be based on a misconception. The model may be substantially wrong. Often use hierarchical model in practice. So I am going to discuss the hierarchical model later on. The general comments are that determination of subjective priors is truly difficult to assess the usefulness of a subjective posterior. Do not be misled by the term subjective. All data analysis involve appreciable personal elements or personal choices. Now, very small, or rather I should say the tiny issue that one can look into, that whenever the unconditional variances are considered, like variance of theta, you see that it is expectation of the posterior variance plus variance of posterior mean. So posterior variance is on average smaller than the prior variance. Reduction is the variance of posterior means over the distribution of possibility. And what the posterior summaries are, one can be interested in mean, median, mode, quantiles, and central 95% confidence interval versus highest posterior density region. I just give you the list for conjugate priors. You know that for binomial Poisson, normal with mu unknown, sigma square known, normal with mu known, sigma square unknown, gamma, alpha, lambda, alpha known, gamma, and then beta, alpha, lambda, lambda known. The correspondingly conjugate prior choices are that. So you know that conjugate priors are the priors for which the posterior belongs to the same family. So this part we devote only on the normal with conjugate prior analysis, and you see that data likelihood is given by the first line. In fact, then if you choose some conjugate prior for mu and sigma square, that leads to the form very similar to the likelihood, and accordingly one can compute the posterior distribution. But this is, one can find the posterior distribution mu given sigma square y to be normal mu n sigma square over kappa n, and sigma square given y to be inverse gamma mu n by 2 and mu n sigma n square by 2. That one can compute easily. One can also consider the semi-conjugate prior. How does it differ from the conjugate prior? It differs in the sense that in the choice for the prior for mu given sigma square, in the case of semi-conjugate prior, it doesn't depend on sigma square at all. So mu and sigma square are totally independently choiced. The prior of mu and sigma square are independent. This is unlike with the conjugate situation where they have the joint distribution. And accordingly, one can compute again the mu given sigma square y and sigma square given y. But the situation is that in that case, sigma square given y is not in closed form. We will see that how we can compute that numerically. One can similarly proceed with a non-informative prior for mu and sigma square, which is proportional to 1 over sigma square, and then one can compute the joint posterior distribution and can get the sigma square given y, the marginal posterior for sigma square, which is inverse gamma, and marginal posterior for mu, which is T distribution. Then comes the concept of simulating from posterior distribution. We know that mu given y, mu given sigma square y is normal mu and tau n square, and sigma square given y, although it is not in closed form, but in the case of conjugate prior it is closed form. So then we, in a very analogously, theta 2 given, theta 2 is marginal, it behaves like sigma square. Theta 2 generated from the marginal posterior distribution of theta 2, and at the mth stage, suppose this is theta 2m, and then theta 1 is generated from the conditional posterior, that theta 1 given theta 2m and y. So analytical steps are to be seen this way, because the last line you can see that the posterior theta 1, posterior density of theta 1 is integration the conditional posterior density of theta 1 given theta 2y and the posterior density of theta 2, and then integrating over theta 2, that gives me the posterior density. So this is the graph of mu versus sigma square, the posterior density, and this is only the mu given y, sort of a T distribution behavior. The comparison between simulation versus exact is that with the exact situations, some posteriors do not have closed form, and some likelihoods are too complex to deal with. The high dimensional problem comes there, and one needs strong mathematical skills to ultimately analytically derive the posterior distribution. In the case of simulation, the limitations are like this. Simulation has stochastic error, one cannot skip that, and one has to look at that how the stochastic error can be minimized, and the iterative algorithms may not converge, sometimes too easy to deal with, so one needs to know the programming language. Then comes the prediction. So this is another part of posterior analysis. One can compute the predictive density of the future observations. I just give you one particular situation in the binomial setup where with n equals to 20, x equals to 12, and the beta prior to be a and b to be 1, you see that predictive density comes out to be of the form. For the univariate normal setup, predictive density can be computed analytically and very simply, and that form comes out to be, this is basically normal density. So predictive density of a new observation is normal with mean mu1 and mu1 given by the posterior mean expectation of theta given y, and variance is sigma square plus tau 1 square. Tau 1 square, once again the posterior variance of theta given y actually. So this is how the predictive density can be computed for the normal distribution. Similarly, for the partial distribution, one can go for the predictive density, and that comes up with the prior for the parameter to be gamma distribution. One can compute the posterior density to be negative binomial, and that negative binomial with the new observation has the predictive density as negative binomial with summation xi plus alpha and 1 over lambda plus n plus 1. We now go for the hierarchical model. It is an extension to the standard prior analysis, posterior analysis. I try to demonstrate that example, a very standard example that tumors are developing on rats, and in several labs they try to obtain through their experiment, try to obtain the chance of developing tumor based on the diets they have been produced and the environment. So the current experiment gives out of 14 tumors in an experiment, only 4 developed tumor. 14 rats in the experiment, 4 developed tumors, and so the previous reports are already at hand. Like you see that in the first row, out of 20 rats, no rat developed tumor. Similarly, this goes on and on, and sometimes we have, like in the last row, out of 23 first element, you have out of 23 rats in the experiment taken, 6 developed tumors and so on, and the last one is out of 24, only 9 developed tumors. So this is a situation that can we use these previous reports to go for our current posterior analysis? That's the basic question that arises. And the binomial likelihood with beta prior is taken to be alpha beta as the hyperparameters. One idea is that each experiment should be treated in isolation. So nobody bothers for that. You start with y1 as the number of rats developed tumor, and this theta 1 is the chance of the population chance of developing tumor. Y2 is in a different experiment, and the chance is theta 2, like this way. So one can do separately the analysis for that also. And another idea is that theta 1, theta 2, theta 3, they are all having the common value theta. So this is in that case one can pool all the experiments. So all these 71 experiments are pooled together to get a better average, to get a better estimate of theta. Now in the rat tumor example, as I am talking about the hierarchical base, is that I can think of the first situation where y1 is the number of rats that develops tumor in the first experiment, and the chance, say theta 1, not known to us. Similarly for y2, and the current experiment is y71, for which we know that we have 4 out of 14 developed tumors, and theta 71 is the chance of developing tumor in the population. So what we do is that in the hierarchical setup, we assume that theta 1, theta 2, theta 3, theta 71 are coming from some population, the hyperparameters alpha and beta, and that hyperparameters may not be known to you, so one need to estimate the alpha beta, or one need to have some prior for alpha beta, and that's how it goes on hierarchically. Now to do that, one need to know that what is exchangeability. Now if you have j experiments, j equal to 1 to capital J, so in our case for this data it is 71, so we have corresponding data set, theta 1, theta 2, theta 71 or theta j is the experiment specific parameters, and the corresponding likelihood can be written as py1 given theta 1 dot dot pyj given theta j. So theta 1, theta 2, theta j are exchangeable IID in the sense that it is invariant, their density is invariant under permutation of indexes. So even if we consider theta say 5, then theta 1, then theta j like this, the probability density form remains invariant under that. So it is exchangeable prior for theta 1, theta 2, theta j. Now ignorance and exchangeability are very in the opposite directions. If no ordering or grouping of parameters can be made, one must assume symmetry among the parameters in their prior distribution, and parameters theta 1, theta 2, theta j are from a common superpopulation determined by an unknown hyperparameter phi. Imagine each group was conducted with mice of different age. Now in the hierarchical model, what is happening is that theta, this phi behaves like alpha and beta as I mentioned previously. So this is the prior for phi and theta, which is pi or p theta given phi and then multiplied by p phi. And p phi, then we can compute the p phi theta given y, the posterior density of the hyperparameter, and theta is something like proportional to p phi theta, p y given theta, like this. So in the rat tumor example, you come back and see that what is happening, that you start from the below, you see that yj given theta j nj is binomial theta j nj, and then you go for assuming prior for theta j given alpha beta, the hyperparameters is beta alpha beta, and then for alpha beta you take some non-informative prior to avoid the subjectivity of the hyperparameters that appear in the prior for alpha beta. So then one can go for joint posterior, which is the product of the likelihood and the prior at the first level and the prior at the second level. So that gives me proportional joint posterior density, which is proportional to the product of these three. And then p theta alpha beta given y is depending on what choice of prior for alpha beta we have taken, and one can compute ultimately the posterior density of theta given alpha beta y. That's a very nice form. It comes out to be of the form beta density, and so one can also get alpha beta prior for alpha beta, posterior for alpha beta given the data, which is depending on the what prior you have taken for alpha beta, which gives me another standard form. And this is basically the final stage, the computation under hierarchical model, where the parameter theta is of interest to us basically, but still phi, which is alpha beta nuisance parameters, they also come into the picture, and often is to provide the simulations from p theta phi given y. So as long as the new computational technique is not presented, let us confine with this thing, simulation technique, that p theta phi given y, which is p phi, p theta given phi, and p y given theta phi, and then determine analytically p theta given phi y. Easy if it is conjugate distribution, then find p phi given y, which is over the integration one can find. And then the simulation technique is you draw phi star. It's like the previously I mentioned that how to go for the simulation. Draw phi star from p phi given y, and then draw theta star from the conditional posterior theta given phi star y. So that is repeated to get ultimately the posterior observations from the posterior distribution. This is the situation of the rat tumor example, and you see that the steps are like this. In one, the posterior density of alpha beta theta has been written. In two, the posterior density of every such theta j is given, and then simulate from p alpha beta given y. That has been elaborately mentioned here. So this is how we can simulate from p alpha beta given y. Find a diffuse prior. Diffuse means prior, uniform prior that blows, that's divergent. So diffuse prior for diffuse hyper prior, prior for alpha beta. So ultimately there is a lot of derivation. One can see that the prior for alpha and beta comes out to be proportional to alpha plus beta to the power minus 5/2, and one can find also the prior for the ratio alpha over alpha plus beta, which is the mean, and delta 1, which is alpha plus beta to the power minus half. The posterior, the prior for gamma 1 and delta 1, that also can be derived in a similar manner. So find the posterior marginal contour plot of the unnormalized marginal posterior distribution, then generate 1000 random samples from the joint posterior distribution. This is how you can see that how it has to be generated. Like first of all, for gamma and delta has to be generated, and then after generation that one can go for generating theta L and can compare the posterior mean and variance based on the generated observation. One can talk about the empirical base also. I just quickly go through that. Suppose you have xi bar, x1, x2, xn from normal distribution and theta and theta I sigma square by n for I equal to 1 to t, and then suppose it is known to believe that theta I follows normal mu tau square, where mu tau square are hyperparameters. This is basically one can think of if theta I is replaced by corresponding linear model type things, you can get a random effects model. So one can get the maximum likelihood solution. Bayes estimator of theta I comes out to be this. Empirical Bayes technique is where mu sigma square tau square, instead of considering the prior for that initially, we get the maximum likelihood estimates are placed there, are substituted in place of mu sigma square tau square, and we can get the empirical Bayes estimator of theta. Now, empirical Bayes estimator is quite cumbersome. As I said, that this is basically a compromise between the theoretical, the hierarchical Bayes and the classical technique. In many situations, it is preferable, especially in the small area estimation and all.
Let me summarize what I have discussed with you in this session. First of all, I considered the prior selection, different varieties of prior. First of all, the objective prior that comes from the standard concept, standard distributional setup and other things. And what are the demerits, what are the merits, we discussed that. And then we little bit pointed out the subjective choices of priors that has quite a lot of limitations, a lot of controversies, disputes and other things. And but people cannot avoid selecting the subjective prior, even in the objective prior also. In at some level people consider the subjectivity. So subjective choices come up automatically. And then we go for the normal distribution setup, the standard conjugate prior analysis, and then we go for the we derive the prediction interval or prediction for new observations based on the posterior concept, and then the credible interval. After that, we extended our idea to the hierarchical Bayes and empirical Bayes setup. In hierarchical Bayes, people consider Bayesian analysis at different levels. At different levels, the priors are considered, and accordingly, the posterior analysis is carried out. And at the empirical Bayes, it is somewhat sort of compromise between the classical and the Bayesian approach, where the hyperparameters are estimated from the marginal distribution of the data and then substituted there in the prior distribution. So posterior analysis is carried out accordingly by the empirical Bayes approach. Now, there is a comparison between the hierarchical Bayes and empirical Bayes, which one is good or bad. That has to be discussed later on. Okay.